So please welcome Magnus Hagander. He is president of Postgres Europe, and he will give a talk about Postgres replication. So give him one hand.
Thank you. I guess you're the crowd who learned that you have to get to all the rooms very early at FOSDEM, right? So you're going to miss the next talks because you're in here. Oh, that one is a little bit too loud. I'll speak a little bit softer. So first, a quick couple of words about myself. As I said, my name is Magnus Hagander. I work for a company called RedPill, which is an open source services business in the Scandinavian area. I'm based out of Stockholm in Sweden myself. I do a lot of Postgres work there, sort of consulting, training, support, typical open source business. Within the Postgres team, I am a member of the core team. I'm one of the committers on the project, and as mentioned, I am currently the president of Postgres Europe. Any one of you who is a member of Postgres Europe, don't forget that we're about to run elections for next year, so you can vote everybody else off the board. You can't actually vote me off the board. You have to wait 1 year, and then you can vote me off the board. Anyway, we are here to talk about replication. So, does anyone remember this? Does anyone remember the fact that my clicker stopped working? There we go. Does anyone remember this? Right? Who was around back in these days? And then you had this, right? And then with some of us who were sitting there, what about these clusters that I have that are replicating with Postgres, and it just works? But Postgres for a long time didn't have built-in replication, right? We had external replication tools. Some of them were easy to use. Some of them were, as I'd like to put it, actively user-unfriendly, but they worked. And that wasn't, as I say, it wasn't really the case back then that Postgres didn't have replication. It just wasn't very obvious. It obviously isn't the case now. And the case now is also still not that Postgres has a replication. Just like them, there are many choices. There are many more choices now than there used to be. Back then, everything used to be an external replication system that you put into your Postgres. Now there are external and internal options, and we still have to choose for them, right? And you have to pick which one to use. Or, in fact, you can pick more than one, depending on exactly what your requirements are. We still have some that are hard to use. We have some that are very, very easy to use. Now, when we do replication, we can do it at sort of many, many different layers, usually to solve different problems, sometimes to shift blame to somebody else. There are many different reasons to do it. Everything starting at the hardware, well, like hardware is also software, right? But at the things that are sold to us as if they are hardware, which is software that somebody else wrote and called firmware, all the way up to actually doing the replication completely in your application and just run across sort of separate databases. So I like to put this through, we have application level replication. We have what I call app in database level replication, which is basically trigger based, right? It's basically an application that runs as triggers inside of your database. You can write it yourself, or you can use something else. Back in the days when this whole Postgres doesn't have replication was the truth, then this is basically what Postgres had in the form of 4 or 5 external different projects that would do it. Now we can do database logical replication. We can do database managed physical replication. We can do operating system replication, which at this point is basically things like DRBD or similar solutions that run transparently in the that try to run transparently in the operating system. And then of course at the very end we can do the hardware-based replication, which today basically means a SAN, right? So let's go through this stack from the bottom and see what options we have in the Postgres world today. At the very bottom end, like the lowest thing that we can do here is a SAN-based replication. This is basically your hardware takes care of the replication. It is typically a block level replication handled by whatever firmware is running in your SAN. It is transparent to the operating system, and that's the whole point of it. Right? In the OS, you get a block device, and you have the same block device somewhere else, and it's all just magic. And as Postgres runs on top of file systems, well, you mount your file system on this block device, and you automatically have a replicated solutions where you can well, usually you can't mount both at the same time, but you can mount it at, for example, a different physical location and fail over your database there. This is very common today, I think, in the scenarios that I work with our customers in, like larger enterprises. Everybody has this one way or another, especially in the world of virtual machines. And I'm sure most of you have at least at one point used a virtual machine, right? You probably know what this is now. And most enterprises use nothing else, right? There are all these massive, like, VMware cluster things. So it's a pretty common thing. It's a pretty simple thing. You can do this sort of anything from just a single rack replication to multi-site, synchronous. And the good thing about these is that these solutions are sold to be guaranteed to never fail, right? Because they're multi-sites and they're following all the best practices and things. And of course, things that never fail are perfect, right? Yeah. Most people I know who relied on this for their database replication have had big problems with it, simply because there is no such thing as something that never fails. It's only a matter of when it fails, and if everything fails at once or only some pieces at any given time, right? It does work as long as it works, but when it fails, it tends to fail in a very spectacular way because it takes everything down. And what I unfortunately see is a lot of people are building is their database was not the only thing that was built entirely on the fact that this storage can never fail. I've seen scenarios where people lost some 6,000, 7,000 virtual machines at once, and suddenly the fact that they also lost their 5 Postgres databases was maybe not the biggest problem in the world. But so this works to a level. But it's the whole thing. If you design everything you build against one thing that cannot possibly fail, it gets really painful when it fails. And it really is a when. There is no such thing as things that don't fail. It's also not very Postgres specific, so we're not going to spend a lot of time on that one. We're going to move up the stack instead and look at the operating system level. And at this level, we're basically, DRBD is probably the most common one, at least if you're in the Linux world. There are some other options around it. And they're basically doing the same thing as this replicated SAM, right? Except they're doing it in the form of a driver in your operating system, instead of being a driver in somebody else's operating system, which is really what your SAM is, right? It's still just software. It works and fails in sort of the same way as your typical SAMs. It has usually a lot less performance, but if you're only worried about hardware failure of your hard drives, it's not a bad choice for a system where you don't need high performance, right? But it replicates your disks over TCP and it replicates them at a block level, so it doesn't know what data it's replicating. That obviously can get pretty inefficient when it comes to performance on the replication side. And again, it's not very Postgres specific. So we're going to skip past that one as well and see what do we have further up the stack in Postgres. So now we're getting to the actual Postgres side, right? Database physical replication. This is a transaction log or WAL-based replication solution. In Postgres, we had this in Postgres 8.3, which is quite a while ago. People were still saying that we didn't have replication in 8.3, and in fairness, it wasn't excellent. It was file-based. So basically, the replication block was blocks of 16 megabytes worth of transactions, which is kind of not very real-time. But it worked pretty well, and this is the foundation that the sort of core replication options that we have in Postgres today, they're all building on this same foundation. In Postgres 9.0, this was turned into streaming replication, meaning that instead of replicating blocks of 16 megabytes, we would now replicate basically blocks of 1 byte. Replicate transaction log as soon as it's created. As of Postgres 9.1, support was added for synchronous, meaning that you can be guaranteed that when you commit the transaction, it is in at least 2 places. And the system will block and wait until the commit has reached the standby node, or a standby node, before the transaction is released. And the way that this works, particularly in Postgres, which I find very useful, is you can mix synchronous and asynchronous, and you've been able to do that since version 9.1. So you can say that some of your transactions are very important. They need to be synchronously replicated. You need the guarantees that they exist in multiple places before your application proceeds to the next step, whereas some other things are not that important, and they can run asynchronously. And you can run this in the same system. You just, in your transaction, you just set, set synchronous mode equals off, and you get an asynchronous, or set synchronous mode equals on, and you get a synchronous one. Depending on your need, you should, one of them would be the default, and the other one would be the one that you changed into. We added support for quorum commit in Postgres version 10, which is your ability to basically say, well, I have 10 servers and I want my transactions to be on 5 of them before I release the transaction. Or I have 5 servers, I want them to be on 3. Numbers other than 2 is basically quorum commit. 9.6 actually added the ability to have more than one, but they had to be in order. And the quorum commit one in Postgres 10 is sort of the one you really want if what you're looking for is more than 2 nodes worth of synchronous replication. At which point you'll just look at all your servers and basically count how many have received your synchronous transaction. And as soon as enough of them, compared to your configuration, has received it, it's released and the transaction will continue. And there are still things being added to this. The thing that's common across all of these is they're all transaction log based. Right? Basically, as soon as every transaction in Postgres, when it's doing anything, it's first written to the transaction log or the while, and then it's written to the rest of the disk. And this is primarily used for crash recovery. But what we do here is, instead of just using it for that, we ship all these changes to the standby nodes. And they basically run in crash recovery mode all the time. And they just keep recovering, so as the data shows up. And the transaction log, looking at it in the simplest form, is like sending binary diffs of your database saying, hey, change this piece of this disk block over here in this way. And we just rerun that on the other side. So that runs pretty fast. The common thing, again, while level equals replica is what you need. This is all you need to set in your Postgres conf, basically. You need to add a little bit of information into the transaction log to make it able to perform this style of replication. As of Postgres version 10, this is also the default. So you can run all of this out of the box on Postgres version 10. On previous versions, you have to enable it, and you have to configure the minimum number of users that can log in and do it as well. The other things that you want to set about this is the synchronous mode options that you can set it on a per transaction basis, where we have the ability to set it to off, local, on, or remote apply. If you set it to off, that actually means that your transaction will also become locally asynchronous. So if your primary crashes or just reboots or something, you may actually lose your very last transaction. That is running in completely asynchronous mode. It will still guarantee consistency of your database. It'll guarantee everything else, except that you may lose by default about a quarter of a second worth of transaction worst case. Obviously that's tunable, but something in that area. If you set it to local, that makes you get your sort of traditional asynchronous replication. Data is written synchronously to the local disk, but it's sent asynchronously over to your standbys, which can be 1 or 20 or 100. If you set it to on, then Postgres will replicate the data, and when you commit, so all coordination happens at the commit level. When you commit on your master, then the data or the transaction will block until the data has been sent and written to disk on the standby. And in synchronous mode, we wait for one standby. If you have 10 standbys, we'll wait for the fastest one of them. And finally, you can also say it in a mode called remote apply, where we also wait for the database on the standby node to have completed the crash recovery of this transaction so that it's actually visible inside of that database. Because on these standby nodes, you can still open transactions. The standby nodes are read-only, but you can open transactions. You can get MVCC snapshots across all your tables. So you may have queries running on old data and things on the standby. So we use them for many different things. And obviously, the further down the list you go, the slower things will be, but the more guarantees you have in the event of a failover of your replication system. And we have the 3 different methods that we can do synchronous. And the simplest way, you set a parameter called synchronous standby name, and you list the names of your standbys. And in this case, I have just S1, S2, and S3. as soon as any one of these have acknowledged that a commit has reached it, your transaction will be released and the application will keep moving on the master node, right? This we've had since Postgres 9.1. The first, which is the one if you just say like this, it's still synchronous standby name, you say in this case 2, parentheses 1, 2, 3. It'll wait for S1 and S2 to finish, assuming that they're online. If one of them goes online, if S2 is online, then it'll wait for S1 and S3. But it'll always wait for the first ones in the list. And then the quorum commit that we added in Postgres 10, then you set your synchronous standby names to any 2 in this case, and it'll just pick whichever 2 of those are the fastest one at the moment. So this way you can say, you're guaranteed, in this case, any 2, well, you're guaranteed your transaction is on the master and on 2 of the standbys. So if your master dies, you still have your data in 2 places, fully guaranteed at all points in that. Again, the common things of these, streaming replication, I would say, for most people who want to do replication in Postgres today, this is what you do. It's very easy to set up. It's pretty hard to get wrong. Personally, I like that in solutions. And in particular, once it's working, right, it doesn't just silently stop working. It's very easy to monitor. There's one thing you have to monitor. You monitor how far behind it is. There's no way that you can lose individual tables or anything. It's either all or nothing. It's very efficient. It's very, very low overhead. And of course, it's built in. Built in is nice. We don't have to go download a separate package or install it from whatever repository we're using or things like that. Getting streaming replication working in a modern Postgres version is really easy. Particularly, again, as we do this in Postgres version 10. You go to, well, obviously you have your master node up and running already. You want to set up your standby node. It's basically 2 commands. First you run the command pg base backup, which will take a backup of your master node. So basically we take the backup from the master to the standby, and then we provision from there. We give it a directory just where we want it, varlib PGSQL or wherever we like to have it. We give it a host name pointed to the primary. It could be an IP address or a host name. We give it a user. It has to log in. For streaming replication, it needs to either be a super user or it needs to be any user that has the special replication privilege, which is normally the recommended one. So use a separate user and that has the privilege to do replication. Then we add the little switch -r, which says this is not actually going to be a backup, this is going to be a replica. And then the system will automatically provision a configuration file that sets it up as a replica. We give it what is known as a replication slot to make sure that that's basically registering the standby node with the master so that the master doesn't delete data that the standby node still needs if it falls behind, if you lose the network or reboot the standby or something like that. And then you can add the little -p thing in the end there, which is just get a progress report. If your database is big, if this thing runs for a couple of hours, it's nice to see how far along it is. And when you've done that, you just start Postgres on the standby node and you're done. If you are using Postgres prior to version 10, you also add to this -x stream so that your replica doesn't fall so far behind before it gets started that it never actually starts. This can otherwise be an issue if you're running it on a very active database. This is not necessary in Postgres version 10 because it's been changed to be the default. But on previous versions added -x stream, and that's pretty much it. It basically sets it up to start replicating before it finishes the backup. It starts replicating immediately so that it doesn't fall so far behind that it might not be able to catch up. There are a few limitations, obviously, of this one. It's architecture and compile flag dependent, so you can't freely mix different compilations of Postgres, different platforms, like between Spark and Intel, or Windows and Linux, which kind of works, but it's not really supported. It's whole cluster only, which is the thing that bites most people, right? If you have 10 databases, you have to replicate all of them. It's the entire cluster of all of them are being replicated. And your standby node is completely read-only. You can't write anything on it. You can't even create temporary tables on it. Basically, the standby node does not have its own transaction log. So any operation within the system that generates transaction log will just fail. And it's primary to standby only. Right? You can only replicate in one direction. But this is usually not a problem if what the problem you're trying to solve is availability. Right? If you're replicating to gain high availability in your system, then you're probably going to replicate between machines that are roughly equal. They're going to be running the same thing. If you're running Red Hat on your primary, you're probably going to be running Red Hat on your standby. For consistency and things like that, you're going to be running on the same platforms and things like that. But there are other cases where it can be a problem, of course. Streaming replication in Postgres does not come with built-in cluster management. So no manual failover, no automatic failover. It just provides the infrastructure. You can build a failover solution on top of it. All the plumbing is there, all the APIs are there, all the monitoring is there, but it's not shifted in there. And it doesn't support failback. Well, it doesn't support easy failback, particularly if you're trying to build these things yourself. There are some very complicated cases because since the replication, for example, happens at commit level, even a master might be ahead of a standby, even if they're in synchronous, because there might be uncommitted data. And we can't control where we fail. That's kind of the whole, then it's not a failure, really. So it's really easy to get started. But if you want to build really high availability on top of it, it can be a bit harder to be maintained. Of course, that's when we can turn to these outside support projects. There are cluster management solutions for Postgres. They're just not built in. There are a couple of good ones that I would say are the ones that you should evaluate today. There is a management tool called Patroni. It's designed to be automatic from ground up. There are some others that were designed initially to be manual and then sort of upgraded. Patroni is designed for automatic failover management, automated pretty much everything. It can plug into multiple different consensus stores. It can use etcd, it can use Zookeeper, it can use Console. I believe the latest version, which I think is out now, can actually run without an external one as well. And it has nice plugins to, for example, it ships with patterns for integrating with HA proxy. So you just you point your application at an HA proxy, and Patroni will control your Postgres nodes. It'll control your HA proxy, and everything just works. Well, until it doesn't. Of course, that's true of every solution. But Patroni works pretty well, and it's by now, I'd say, it's a very well-tested solution. The other big option that we have in the Postgres world today is a tool called Rep Manager, or Rep MGR. This is one of those that was originally designed to handle replication clusters but with manual, and has later learned to do automatic failover and things as well. I found it traditionally it's easier to use than Patroni when it comes to dealing with manual failovers, because Patroni wasn't really designed to do that. So if you want to do that, and I mean, we can spend a whole other talk just discussing about whether automatic failover is actually a good or a bad thing. That will depend on your situations. We're not going to do that now. But Rep Manager is capable of doing both of them. It doesn't handle connection management in itself. It has like plugins where you can have it run external commands to reconfigure things. You can still use it with things like HA proxy and just have HA proxy pull your database, make sure that it works. But it can take a little bit more integration for those things. But the advantage there, of course, is you gain a little bit more flexibility when it comes to those things. And finally, I'll point out there is a tool called PAF, I think. It's the Postgres Automatic Failover. It's resource agents and configurations and plugins if you're using a Pacemaker and CoreSync. One of the strong points of that one is, well, if you're using Pacemaker and CoreSync to manage other things in your organization, other types of HA clusters, then the configuration is obviously very similar. It's something that your operations people will be comfortable with and using things like that. And the traditional way to set up here is, well, you set up a virtual IP, and the Pacemaker CoreSync combination will move the virtual IP as necessary to whichever node happens to be the master node again. And again, well, it's called Postgres Automatic Failover. Its focus is doing manual failover, of course, or maybe automatic. So if you need to build like a high availability cluster, these are all very good options. There are some other options out there as well, but today these are sort of the main options that you will find throughout the Postgres world. So if we keep moving up the stack, database logical replication is the next level. Right? This is that many of you probably know, it's new in Postgres version 10. We actually added a lot of the infrastructure already in Postgres 9.4 with something called logical decoding. And then it's been built on that up until Postgres version 10, which is the first version that released with built-in actual replication sitting on top of this. Now this still piggybacks on the write-ahead log, right? It still sits in the transaction log, which means it's still very low overhead. It's a little bit more overhead than your physical replication, but not much from a performance perspective. It can be a lot more overhead from a management perspective. But since it's in the transaction log, well, we just change. Instead of saying while-level replica, we move to while-level logical. And now we have logical replication. It's almost that simple. Then you need to set up a few things. Now the way that logical replication works is it reconstructs the changes on a per row basis. So it's not one of those solutions that actually replicates your SQL statements and runs them again on a master, but instead of just sending the binary differences, they send the logical differences saying, well, I replace the row that's identified by this with this new content, and does it on an individual row basis. It's still fully transactional. So it's still integrating with that, and that's one of the main reasons why it can use, or one of the good reasons it uses the while to make sure that that's where you have your commits, and it can trigger things directly on the commits. Now, being on a row basis instead of being binary across the whole cluster means that you can do table-level partial replication. Right? You don't have to replicate everything anymore. You can say, I just want to replicate this one table over here. And you can also pretty easily do what I like to call table bi-directional replication. It's still easy if you say this table is going to replicate from node 1 to node 2, and this other table is going to replicate from node 2 to node 1. Like we might have a master node for each customer depending on location, and we just replicate them in two different ways. And then we have a view on top of it, or it can be partitions or something like that, which the application works. There are many scenarios where actually just being able to do table-level bidirectional replication can be really, really useful. And of course, logical replication is slightly more complex than to set up than it is to set up physical streaming replication, but it is still very simple. Just as an example here, on your master node, well, which will then be master node for this particular table, you create a table. Every table has to be identified. In this case, if your table has a primary key, it will replicate based on the primary key. Then you create this thing called a publication. I say create publication test pub for this table. It can be multiple tables. You can also say for all tables, and then it will dynamically add new tables and things like that. A publication is the unit of replication. So if you put 10 tables into a publication, they will replicate as one unit, and they will sort of move over together. And these are things you need to consider, for example, if you have tables with foreign keys between them. You can't replicate the changes to just one of them. Then it's one of those funny things that might work most of the time, but not all of the time. And you want there. So those are things you need to consider. These are the cases where logical replication can become a little bit more complicated. Then on the standby node, you create the same table, maybe using something like pgdump in schema mode, and then you create a subscription, which is the other side of this. So you say subscription, test sub, connection, and this is connecting to the database where we created the publication, and then we just say publication test pub. And this test pub here is, of course, that, the same one that we created over here. And as soon as we create this publication, as soon as we create this subscription, replication of this table will start. And it will start doing it on a row-by-row basis. So as soon as I insert a row, it will get replicated over to the other one. Now, logical replication comes, of course, with its own sets of drawbacks in this. It doesn't currently do anything other than data replication. It doesn't do schema replication. So if you do alter table, you have to remember to do alter table on all the nodes. And you have to do it in like the right order and things like that. Bad things can happen otherwise. It doesn't, particularly it doesn't replicate sequences. So if you have your table with a primary key based off a sequence or a generated by column or something like that, then the values will of course replicate. But the sequence will still be stuck at 1. So if you use this for something like high availability and you fail over, then all your sequences are going to be wrong. Which is kind of like, oops. So it's not very good for high availability replication. Now there's no reason that we couldn't be able to add things like schema replication and sequence replication on a fundamental level. We just don't have them today. But that means that today this is really good for data distribution and is not very good for high availability. So it really depends on the solution you have. We also lack something that is called failover slots, or well, one of the guys working on them called them failover slots. The general idea being if you're replicating from a master with logical and physical, and then you fail over to your physical standby, your logical replication will not follow. So there are still things that need to be done when it comes to the database level logical replication. But the built-in one is still very good, and it covers a lot of people's use cases, but it's not complete. Now if you want to build further on logical replication in the database, there is an extension for Postgres called PGLogical. This is basically an external version of the same thing. It's where it started. It's been merged sort of piece by piece into what is now the logical replication in Postgres version 10. And more pieces of it will be merged into future versions of Postgres. But they have more capabilities today. But it also means that it's less integrated and it's a little bit more tricky to work with. You don't have these nice commands. Instead you call functions for everything, and there are a few things that are where the docs are like, you have to do this in the right order, otherwise, dragons show up. But it does support sequence replication, for example. It does support row-based filtering. So you can say, I don't want to replicate the whole table, I only want to replicate rows that match this. You can do column-based filtering, saying, I only want to replicate these columns and not the other ones for it. It supports merging and conflict resolution, so you can have multiple nodes replicating into the same table in a destination, for example, or you can have local changes to a table and replicating into the same one, and you can define ways for what's going to happen when there is a conflict. Because if you write from more than one place, there will eventually be a conflict. You may think that your application prevented that, but it didn't. It did in testing. It always does in testing. And there are a number of other things that PGLogical adds on top of this. PGLogical also supports Postgres 9.4, not just Postgres 10. And using PGLogical, you can accomplish what's basically, well, there's no such thing as zero, but very close to zero downtime upgrades by using logical replication, because physical replication was tied to specific Postgres versions, right? Versions and platforms and compile flags and things. Logical replication isn't. You can, using PGLogical, you can replicate from Postgres 9.4 to Postgres 10, for example. Now you will be able to do things, mostly these zero downtime upgrade things, probably using the Postgres built-in replication as well, but only from version 10. And we haven't released version 11 yet, so you'll have to wait a while for that one. Now if we continue further up the stack, we have the app in database, right? This is the old trigger-based replication systems. And the big ones of those are still out there, right? Anyone ever deployed Slony? Did you like it? Okay, yeah. Well, there's always one. Slony is a really capable system, but it's not very easy to work with. And unlike the other ones, it is actually really easy to break. And when you do, you're in for a lot of pain. But it does things, and even today, even with PGLogical, even with all the built-in stuff, there are things that Slony can do that they can't. You can set up really, really strange things in your application with Slony. And it works pretty well. We have Bucardo and Londiste, which are also trigger-based systems that are basically simpler to use than Sloaney. I think that's their main selling argument. It's really that they're much easier to use than Sloaney. And they still are. They're still good choices for cases where the other solutions don't apply. But they're not really your primary target. For a long time, they were the only one we had. They had a lot more overhead. Every time you do an insert, it's copied somewhere. And this is all happening in triggers running in user space in the database. And then you pull it out and you delete it. And these tools all do sort of all sorts of weird things to make sure the overhead is as little as possible. But it's still going to be much, much worse than for the logical or physical built-in resolution. But there are complicated scenarios where you really need to do it. Such as, who in here likes multi-master? Everybody wants it, right? Everybody really needs multi-master. That's my experience. Everyone needs it until they start looking into what they really need. Or in particular, until they start realizing what it means. Because what most people want when they say they want multi-master is they want transparent multi-master, right? They want their application to remain completely unchanged and things to just magically work. Unfortunately, we don't have a lot of magic. There are things in play here like the speed of light and annoying things like that we haven't figured out how to deal with yet. If you're doing a database in the form of your traditional relational database, you cannot do transparent multi-master. Like there are people who sell it. Who's ever met, for example, a salesman from somewhere who wants to sell you a solution based on Oracle RAC saying it's transparent multi-master, it'll scale everywhere and it'll work perfectly? Anyone ever met a guy who tried to sell them that? I know I have. Yeah, did you try to deploy it? Did it work? It doesn't work transparently. Now, don't get me wrong, RAC, using a RAC-adapted application can do some very good things. But if you just take your regular application and point to it, very bad things can happen. And the same goes for all solutions. So the completely transparent multi-master just doesn't exist if you want the consistent database of your traditional relational database system. Now, there are some options within Postgres still. There is a toolkit, or a fork actually of Postgres called BDR that has been developed a lot together with the PG Logical stuff that does support geographically distributed multi-master. But you're not going to, if you are, let's put it like this, if you manage to actually run your application completely unmodified against it, then you probably didn't need multi-master. Right? It goes for most solutions. But if you engineer your application to work together with a solution like BDR, yes, it can solve those problems. In a lot of cases, probably not all of them, but in a lot of those cases. Now, BDR today is a fork of Postgres. It's not an extension, it's an actual fork of Postgres, which I think is based on 9.4 or 9.5 at this point. They're working their way towards newer versions. I think the plan is, last I heard, to still make it into an extension. In the next major version of BDR should hopefully just be an extension on top of Postgres, but it's not there now. But we'll hopefully get there. Of these trigger-based solutions that we saw, Bucardo supports doing multi-master. The big problem with doing, because all of the trigger-based ones are asynchronous, and the big problem with asynchronous multi-master is, of course, you will eventually get conflicts. And you need to decide what's going to happen when you get a conflict. Right? Who's going to win? And if you can define those, you can define like very complex policies for dealing with that in a tool like Bucardo. But you have to actually do it. Otherwise, once you run into the conflict, everything just stops. And that's probably not what you intended. But my general recommendation when you're looking at something like multi-master is, first look about 5 more times to see if you really need multi-master. Because when we're talking about these things that were easy to break, yeah, that'll be easy to break in most scenarios. It is a much harder problem to solve than most people realize if you want to maintain the consistency part that really is our relational database. And of course, we can build our replication all the way up in the application itself. and just connect to 5 different databases and run things in 5 different databases and commit them in all of them, and everything will be fine, right? But actually doing transaction control at this level can become very complicated, and you're moving a lot of complexity into your application. If what you're looking for is consistent replication, which is probably why you're using a relational database in the first place, then trying to build that in your application is probably not a very good idea. It's setting yourself up for having to maintain something that will become really, really complicated over time. So, what do we take from this? There are obviously more options than this around, but there are a couple of main things that we want, like main problems that we want to solve with replication today. If what you're looking for is solving the problem of high availability, then you should really just be using Postgres built-in streaming replication. Easy to set up, hard to break. These are very good properties when we're talking about building for high availability, because if it breaks, it will always break in the wrong moment. We know that. That's how it works. And use the fact that you can mix synchronous and asynchronous replication in the same cluster or even between the same nodes. Because by doing that in an intelligent way and in a controlled way, you can get most of the important benefits from doing synchronous replication with almost none of the overhead by simply indicating the important things versus the slightly less important things. Because even on the slightly less important things, we're not talking about losing a lot of data, right? In asynchronous mode, we're still talking about losing a lot less than 1 second worth of transactions, which in a lot of applications really isn't that much, but it's very much more than 0. Like, we've broken the Boolean of 0 and saying it is actually okay to lose a few transactions. But if we mix those, we can get a very good performance through it. And if you want to build, like if what you're setting up is just going to be manually maintained replication, then the built-in tools do a pretty good job. If you want to go a step beyond that, you need to look at things like automatic failover. Don't build your own solution for automatic failover. Look at primarily Patroni and Rep Manager. Compare how they work to what matches your organization. They're both fine tools. They work in slightly different scenarios. I would recommend that you evaluate them both. Look at path if you are already using things or for other things going to be using things like Pacemaker and ChorusSync. If you're not doing that, then it's an extra piece of infrastructure that you're bringing in. You're probably better off looking at these tools to deal with that. But if you're building high availability, don't use logical replication. Don't use PG logical, certainly don't use the trigger-based ones. Who's still using one of Sloaney, Bucardo, or Logiste actively in the organization? Okay, that's fair enough. Are you looking at replacing them? Yep. Or are you happy with them? Anyone using them and not planning to replace them? Okay, yeah. Is anyone using anything that they're not planning to replace? Well, officially, yes, right? Because at some point your project has to officially be finished. The other use case that we might need to cover is read query offloading, right? And if all we really need to do is offload pure read queries, then we can still use physical streaming replication. Because our standby nodes are available, our standby nodes are read-only, you can still get multi-table and multi-statement transactional snapshots on your standby nodes. They just have to be completely read-only. Which goes back to the previous one. Yes, you might want to look at management tools and things like that, but having this set up really easy and really stable, that is a good choice in many cases. Another data distribution, which is different in that now we don't just need to run simple read queries on our data. We might need to replicate different data to different places. We might need to generate temp tables, generate reporting tables, and things like that. Well, if you're using Postgres 10, use logical replication. If you're not using Postgres 10, then why are you not using Postgres 10? You should upgrade. You should use Postgres 10. But if not, look at PG Logical if you're using Postgres 9.4 or newer. Also look at PG Logical if the built-in one isn't good enough for you. If you need the partition replication, for example, replicating some columns or some rows only, then look at PG Logical. And yes, if you're using Sloaney, you should probably look at upgrading your way out of Sloaney. unless you are one of the people who are in one of these use cases that really only Slowney solves, then you're going to keep using Slowney. Just be careful, because it's easy to break. But these are all good ways of dealing with your data going out in different ways. Well, what if you need both, right? What if you need both high availability and read query offloading? Well, do both. Just put up another node. It's a very common scenario that you say you use synchronous streaming replication between a high availability cluster of, say, 3 nodes, and then you also use asynchronous replication to another node or 2 other nodes where you run your read queries, for example. You can freely mix and match these different types of replication. All the streaming ones support that you have cascading replication, so you replicate from node 1 to node B and then from node B to node C, D, and E. So you can replicate into read clusters that then, or into a distribution node that replicates into many read clusters to conserve on network bandwidth, and all sorts of things like that. So in many cases, if you move beyond the simplest needs, you're going to want to mix different ones of these, but these should all be sort of the base points of where you want to go for those things. And that's all I had. Do we have a couple of minutes for questions? Yes, we have 3 minutes for questions. Who wants to be the first one? So, anybody? Yes. You get to run to right in the middle and then throw them. I think, yeah. I think she might have not turned it on for you. Anyway, so the question, I think, is how much latency is added by turning on synchronous replication? And if the application ends up being blocking all the time. It really depends on the distance between your nodes. If you're replicating like close, these are 2 nodes in the same data center or so, then there's a little bit of latency, but it's very, very low. Obviously, if you're replicating across the Atlantic, well, we have to go there and back, right? I've seen a lot of scenarios where you're replicating between 2 data centers that are in the same city, and usually like the overhead is, or the latency overhead is low enough that you barely notice it. Now, if you have an application that's just rapid firing very, very small transactions, yes, you will notice the latency shift there, of course, but most of the time you have multiple concurrent things and things like, and there are a lot of optimizations to minimize it. Do you have a question? Okay. That's a bummer. Does anyone else have a question for Slowney? Oh, hello. Anyone else? The one right there? Yeah.
Just a great presentation. Learned a bunch. One comment or question. The read replicas.
Yes.
Being 100% read only. That is a slight issue because in other databases I put extra indexes on my read replicas, and I don't seem to be able to do that in Postgres, or I might have got it wrong.
So the question is, read replicas, can you create separate indexes on the read replica? And if you're using the binary streaming replication, then the answer is no. You can't. You are unfortunately correct in that you cannot do that. Now, if you're using logical replication, then you can put separate indexes on the receiving side. But in the physical replication, you cannot. It's completely read-only. Anyone else? Okay, well, in that case, did we have one? Yes. Hey, everyone who asks questions are in the middle. That's just to give us a challenge, right? I'm sorry? PG pool. On the replication side of PG pool, my opinion is don't use it. Now, if you put PG pool in front of a streaming replication cluster, for example, to have it handle that's a different story. That's a usable thing, but it also has the ability to do like statement level replication in PG pool. And yeah, my recommendation that really is don't use it. But the rest of PG pool is much better. Time out. Okay, thank you very much.